Okay guys, so today we are going to look at Gaussian law, and we'll look at the basics. From there we're going to answer some questions from the year 2025 to 2024 and 2025. So to start with, let's first understand what it means by electric flask. So we have to understand electric flask. Okay, so electric flask just simply means the number of electric field passing through a Gaussian surface. So the formula mathematically is computed as electric flask, which is phi, okay, phi E. Okay, so phi E is equal to electric field times the area. Since we are saying electric flask is the number of electric field passing through a Gaussian surface, so we multiply the electric field then times the area. Okay, where in our previous lessons we had we said the electric field, we have two formulas of electric field, which is E. So electric field basically is just force per unit charge. Okay, then we also talked about the electric field at a point charge, and we said electric field at a point charge is equal to K Q over R squared. Okay, so we have these two formulas for electric field. So here now we are talking about electric flask, the number of, or the total number of electric field passing through a Gaussian surface. So there are some surfaces which will be at an angle, and when a surface is at an angle, we apply, for example, we are going to have a Gaussian surface, for example that. So if we have, I hope you are able to see. Okay, so if you have some electric field passing through this Gaussian surface like that, then we always assume there is a perpendicular line to the surface. So a normal line which will be perpendicular at 90. Okay, my line is not that clear, but let's assume it's at 90, it's making it 90 degrees with the surface. Then we have that. So we are going to have an angle there, which is theta. So we are going to have an angle. So when we have an angle, the general formula for electric flask would be phi E is equal to the electric field times the area. So since the electric field is acting at an angle, okay, the surface is at an angle, we are going to say cos theta. Okay, so when the surface is not at an angle, okay, which means our theta is 0. For example, if we have a surface which is somewhere like that, that's a surface, but assume it's in 3D, okay, in 3 dimensions. So if you have an electric field there, and there passing through this surface, so which means we are going to have our normal line there, so that will be our normal. So which means here our angle, which is theta, is 0. Okay, so when theta is 0, when you replace here, what will be our cos 0? Our cos 0, when you compute on the calculator, you find that cos 0 is 1. So therefore we are going to have our electric field as EA when theta is equal to 0. Okay, so basically this is the general formula for electric flask. So we can have an angle for 0, 180, When it's 1, to give us -1, so they are going to have a negative. Then we can also have when this is at 90 degrees. So at 90 degrees, when you have, for example, a surface which is for example like that, you have this surface, then we have the normal line, then you have some electric field passing through that surface. Okay, so here our theta is equal to 90. So when theta is equal to 90 degrees, cos 90 is 0, so which means our electric field, our electric flask will be 0. Okay, so when the electric field is perpendicular to the normal, we are going to have a 0 electric flask. Okay, so these are some of the principles we have to use and we have to know. So now I'll jump on Gaussian law. Okay, so let's talk about Gaussian law now. So now Gaussian law comes in whereby there are some surfaces where we can't find the area. Okay, the area can't be found, so we apply Gaussian law to find the area of, we apply Gaussian law when we are unable to find the area of that surface, because we can have some surfaces which are not, they don't have a definite shape. So we apply Gaussian law, and it states that the total electric flask, so the total electric flask passing through a Gaussian surface or a closed surface is equal to the net charge, of that surface divided by permittivity of free space. So basically, mathematically, we are saying the total electric flask, okay, of passing through a Gaussian surface is equal to the net charge. Okay, so Q net, then we are dividing with what? Permittivity of free space, which is epsilon naught. So that's what we have in there, where our epsilon naught, which is the permittivity, is 8.85 times 10 to the power -12. Okay, so it's a constant number which you have to know, but sometimes it's given in the exam. So the SI unit is coulomb per meter squared per meter squared, then Newton. So this is the unit for epsilon naught. Okay, then the unit for electric flask is just Newton. Okay, so Newton dot meter squared per coulomb. So these are the units for electric flask. Okay, so here, since we have multiple units, apply this principle whereby we separate the units with what? A dot. Okay, so this is the formula for Gaussian law, which you have to know. So now we're going to talk about some applications of Gaussian law related to electric field. Okay, so the application of Gaussian law based on electric field. So the first thing we are going to talk about is a sheet. Okay, so when you talk about a sheet, in some books it's written as a planar symmetry. Okay, so when you are asked to find the electric field of a sheet or a planar symmetry, there is a certain formula you have to consider for electric field, not the usual one which we know. So under Gaussian law, we use the formula which is E is equal to, so we have this symbol which is the surface charge density or linear charge density. So in some books it's called surface charge density, but I prefer calling it in area charge density. Okay, so over to epsilon naught. So this which is more like a 6 but not usually a 6, it's not a 6 but it looks more like a 6. So it has a formula, so we are calling it as area charge density. So the last thing which I'm saying area charge density, so I'm going to say the area charge density is equal to the charge, which is my last word, then divide by the area. So it's called the area charge density. So you just swap for what I'm trying to say here. So that's the best way you can remember it. So it's area charge density. So area charge density. So the charge comes first, then the area, seconded by the area. So that's the formula, and this you can also find the total charge. Okay, so this is the net charge by just driving the formula, making Q the subject, saying that multiplied by what's the area. So you can also find the total charge using this when you formulate it like that. But basically, this is the formula for electric field of a sheet. Then the units for area charge density is coulomb per meter squared. So whenever you are given a question, concentrate on the units if given. Okay, so that you know which formula to use. So that's for a sheet. So let's look now for a formula for a wire or cylinder. So now we're going to discuss about the formula for electric field of a wire or cylinder. So the formula which we apply here is E representing electric field, then multiplied by what we are calling linear charge density. So for a sheet we are calling it area charge density, but for a wire it's linear charge density. So the symbol is lambda. Okay, then over, so since it's a cylinder, the best way you can remember this formula is by maybe writing the circumference, the formula for circumference of a circle, so which is 2 pi r, like that. Then you just add what, the permittivity, like that. Okay, so this is the best way you can remember this formula. So you write the circumference of a circle, then you add the permittivity there. So this is the lambda, which you are calling linear charge density. Okay, so this is the linear charge density, and the formula for linear charge density, like we did on area, we are going to say linear charge density. So the charge will come first. So linear, think of it as a line. Think of it as a line, and you can also think of it as a distance, but in this case I'll take it as a length. Okay, I'll abbreviate it with letter L to represent length. So this is the formula for electric field of a wire or a cylinder, if you have been asked to find electric field using a wire or cylinder. So we are moving on to, so the SI unit for lambda, which is linear charge density, is coulomb per meter. So these are the SI units for that, and the SI units for E, when you find your answer here, the SI unit for E, it is just force per coulomb. Okay, for electric field it is force per coulomb. So let's move on to finding the electric field now of a sphere, if you have been given to find the electric field of a sphere. Okay, so the electric field of a sphere is the same as the electric field of a point charge. So we said the electric field of a point charge is equal to E K Q, then over what, R squared. Okay, so it is the same with the electric field of a point charge from even the previous classes we have been having, we have been using this formula. So now we'll proceed on from the sphere. You have to know now the area. Okay, so the area of a sphere is 4 times the area of a circle. So the area of a circle is pi r squared. So 4 pi r squared, that's the area of a sphere. So basically this is where Gaussian law was derived from. Okay, so let me just show you what I mean. So we said electric flux, which is phi E is equal to electric field times what, the area. So here, if I maintain this, I say what's the electric field of a sphere, I'll replace here, which is what, which is 4q r. Then what's the area? So you have to replace the area, which is 4 pi r squared. Okay, so when you replace like that, we know our k, so you have to replace your k there. So I'll say phi E is equal to, so okay, it's 1 over 4 pi, so it's pi E epsilon naught. So from here, what are we going to make a q? Then we have our r squared, and we are going to have that, which is 4 pi r squared. Okay, so we're having something like this. So from here, we're going to cancel out the right thing. So we have this, I can also see it here. Then what else? I have r squared, I can also see it here. Okay, so I'll multiply what I'm remaining with. Okay, so I'm remaining with phi E will be equal to q, then over what, epsilon naught. So this is the net charge. So this is where the Gaussian law formula came from. Okay, so in some books you find another formula for electric field of a sphere. Yeah, the one which has a cube somewhere down there, but all in all they are the same. Yeah, I prefer using this one. So in the next video we are going to solve some questions using these principles. Okay, 2024 and 2025 question paper.